Alright, welcome to another episode. This is still lesson 1, but it's 101.2, which is about booting the system. Introduction. In order to control the machine, the operating system's main component, the kernel, must be loaded by a program called a bootloader, which itself is loaded by a pre-installed firmware such as BIOS or UEFI. The bootloader can be customized to pass parameters to the kernel, such as which partition contains the root file system or in which mode the operating system should execute. Once loaded, the kernel continues the boot process, identifying and configuring the hardware. Lastly, the kernel calls the utility responsible for starting and managing the system's services. Note: on some Linux distributions, commands executed in this lesson may require root privileges. BIOS or UEFI. The procedures executed by x86 machines to run the bootloader are different whether they use BIOS or UEFI. The BIOS, short for Basic Input/Output System, is a program stored in a non-volatile memory chip attached to the motherboard, executed every time the computer is powered on. This type of program is called firmware, and its storage location is separate from the other storage devices the system may have. The BIOS assumes that the first 440 bytes in the first storage device following the order defined in the BIOS configuration utility are the first stage of the bootloader, also called bootstrap. The first 512 bytes of a storage device are named the MBR, master boot record, of storage devices using the standard DOS partition schema, and in addition to the first stage of the bootloader contain the partition table. If the MBR does not contain the correct data, the system will not be able to boot unless an alternative method is employed. Generally speaking, the pre-operating steps to boot a system equipped with BIOS are: Step 1, the post power on self-test process is executed to identify simple hardware failures as soon as the machine is powered on. Step 2, the BIOS activates the basic components to load the system, like video output, keyboard, and storage media. Step 3, the BIOS loads the first stage of the bootloader from the MBR, the first 440 bytes of the first device, as defined in the BIOS configuration utility. Step 4, the first stage of the bootloader calls the second stage of the bootloader, responsible for presenting boot options and loading the kernel. The UEFI, short for Unified Extensible Firmware Interface, differs from BIOS in some key points. As the BIOS, the UEFI is also a firmware, but it can identify partitions and read many file systems found in them. The UEFI does not rely on the MBR, taking into account only the settings stored in its non-volatile memory and VRAM attached to the motherboard. These definitions indicate the location of the UEFI compatible programs, called EFI applications, that will be executed automatically or called from a boot memory. Okay, so the UEFI is different from the BIOS in that it does not rely on the first 440 bytes of a storage disk, also known as the MBR. Instead, it relies on settings stored in non-volatile memory attached to the keyboard. Those settings are found within a um, those settings can be read uh, even if they are part of a partition and they don't have to be a particular file system. It can support multiple file systems, unlike the MBR, where it has to be, there aren't as many options. So UEFI has more options for uh, file systems. It can be on uh, partitions, um, and but it exists on the non-volatile memory attached to the keyboard or attached to the motherboard. These definitions indicate the location of the UEFI compatible programs, called EFI applications, that will be executed automatically or called from a boot menu. EFI applications can be bootloaders, operating system selectors, tools for system diagnostics and repair, etc. They must be in a conventional storage device partition and in a compatible file system. The standard compatible file systems are FAT12, FAT16, and FAT32 for block devices, and ISO-9660 for optical media. This approach allows for the implementation of much more sophisticated tools than those possible with BIOS. The partition containing the EFI applications is called the EFI system partition, or just ESP, which stands for EFI system partition. This partition must not be shared with other file systems like the root file system or user data file systems. The EFI directory in the ESP partition contains the applications pointed to by the entries saved in the NVRAM. Generally speaking, the pre-operating system boot steps on a system with UEFI are: Step 1. The post power on self-test process is executed to identify simple hardware failures as soon as the machine is powered on. Step 2. The UEFI activates the basic components to load the system, like video, output, keyboard, and storage media. Step 3. The UEFI's firmware reads the definitions stored in NVRAM to execute the predefined EFI application stored in the ESP's partitions file system. Typically, the predefined EFI application is a bootloader. Step 4. If the predefined EFI application is a bootloader, it will load the kernel to start the operating system. The EFI standard also supports a feature called Secure Boot, which only allows the execution of signed EFI applications. that is, EFI applications authorized by the hardware manufacturer. This feature increases the protection against malicious software, but can make it difficult to install operating systems not covered by the manufacturer's warranty. The bootloader. The most popular bootloader for Linux in the x86 architecture is Grub, Grand Unified Bootloader. As soon as it is called by the BIOS or by the UEFI, Grub displays a list of operating systems available to boot. Sometimes the list does not appear automatically, but it can be evoked by pressing Shift while Grub is being called by the BIOS. In UEFI systems, the escape key should be used instead. From the Grub menu, it is possible to choose which one of the installed kernels should be loaded and to pass new parameters to it. Most kernel parameters follow the pattern option equals value. Some of the most useful kernel parameters are ACPI enables, disables ACPI support. ACPI equals off will disable support for ACPI. INIT sets an alternative system indicator. For example, INIT equals /bin/bash will set the bash shell as the initiator. This means that a shell session will start just after the kernel boot presses. Systemd.unit sets the systemd target to be activated. For example, systemd.unit equals graphical.target. Systemd also accepts the numerical run levels as defined for sysv. To activate the run level 1, for example, it is only necessary to include the number 1 or the letter S, short for single, as a kernel parameter. MEM sets the amount of available RAM for the system. This parameter is useful for virtual machines, so as to limit how much RAM will be available to each guest. Using MEM equals 512M will limit to 512 megabytes the amount of available RAM to a particular guest system. Max CPUs limits the number of processors or processor cores visible to the system in symmetric multiprocessor machines. It is also useful for virtual machines. A value of 0 turns off the support for multiprocessor machines and has the same effect as the kernel parameter no SMP. The parameter max CPUs equals 2 will limit the number of processors available to the operating system to 2. Quiet hides most boot messages. VGA selects a video mode. The parameter VGA equals ASK will show a list of available modes to choose from. Root sets the root partition distinct from the one pre-configured in the bootloader. For example, root equals /dev/SDA3. Root flags mount options for the root file system. RO makes the initial mount of the root file system read-only. RW allows writing in the root file system during initial mount. Changing the kernel parameters is not usually required, but it can be useful to detect and solve operating system related problems. Kernel parameters must be added to the file /etc/default/grub in the line grub_command_line_linux to make them persistent across reboots. A new configuration file for the bootloader must be generated every time /etc/default/grub changes, which is accomplished by the command grub-mkconfig-o/boot/grub/grub.cfg. Once the operating system is running, the kernel parameters used for loading the current session are available for reading in a file /proc/cmdline. Note: configuring grub will be discussed further in a later session. Alright, let's take a look at this file in the environment here. So this is a folder, so this, oh no, this is a file. Okay, that's interesting. So did I get it right? etc default grub. Looks like I did. Yeah, this doesn't have. So this is a different distro of Linux. Let's use Fedora instead. And as it was mentioned, I believe this is just simply the most popular bootloader. So there are multiple bootloaders that can be used. It could be the place that for Alpine Linux distro. Grub is not typically used as the bootloader. Nope, it's saying that it is the standard bootloader. Could be something to do with it being a virtual environment as well. Yeah, it might have to do with that since it's on my home lab. It'll probably show up. All right, system. You know what? I think I'm gonna stop it here. I won't make it through all of this. This is a good time to stop. Alright, so that's the end of the video. Thanks for watching. Stay tuned for the next one.